Hello, my name is Andrew Just, and in this module on the probability weather type methodology, we're going to discuss about the top-down approach. So the review of the top-down idea is that you forecast the environment and the probabilities of precipitation types drop out automatically. Much simpler approach and also easier to update. It consists of 3 grids that you can create and edit as needed. There's data available in GFE from a variety of different model sources, including the MBM, SuperBlend, RapNav, GFS, and Canadian. You can also include road temperatures. And within the forecast builder process, this is step 3, where you access the top-down section. So the first top-down grid here is max wet bulb aloft. This is defined as the warmest wet bulb temperature from 2,000 feet above the ground to 400 millibars. You can find observed values for this grid from both RAOB and AMDAR data. This replaced the max T aloft in August 2016. At that time, when we looked at research here at the ARX office, the max T aloft and the max wet bulb aloft were generally the same, at least east of the plains. However, when you get to the high plains westward, using the max wet bulb aloft perform better for precipitation type performance, albeit there is a lesser sample set for precipitation type cases. One big note here, however, is that at precipitation onset, max T aloft can perform better. In this situation, the hydrometeors feel the presence of the warm air first before it saturates, and so you can end up with a warmer type of precipitation than you would normally expect with a max wet bulb. So on the right side of the screen here, you can see the various types of precipitation and how they map to the max wet bulb aloft. So as you move from 0 to 1 to 2 to 3, you'll notice that you start going to warmer precipitation types from snow to sleet to liquid. These curves were generally based on the Rober et al. 2001 data set, as well as additional ARX research. So a quick example of max wet bulb aloft and what you might see in your GFE, especially as part of the forecast builder process. What you'll notice here in like the bottom left in this max wet bulb aloft grid is values around 4, and if you go back to the previous slide, those represent mostly a liquid type. Then as you get colder, head into the northeast, into southeast Minnesota and southern Wisconsin, that's more of a sleet type situation. And then even farther northeast, you get below 0 readings, and that's just all snow. Now we understand max wet bulb aloft. What can change the type based off of that? Well, one of them would be the prob ice present grid, and this is the second top-down grid. The prob ice present definition here is that probability that ice exists in the clouds. As values decrease to 0, expect your snow and sleet to decrease and your liquid to increase. An example of a loss of ice is depicted there on the right. Observed values for prob ice present can be found in IR imagery as well as RAOB and AMDAR data. So how is prob ice computed? First, there's a check for a deep dry layer. Think cedar feeder, looking specifically for a layer of 5,000 feet deep with a 75% RH. If that layer is deeper and or drier, then any ice crystals that are above there would sublimate and be removed, and then the bottom layer below the dryness will be the only spot that gets evaluated for prob ice. From there, we apply aircraft research to assign a probability based on the RH with respect to ice for temperatures minus 8°C and colder. And here's an image representing that curve from the aircraft research that you can see at minus 8 you're looking at 30%, but by the time you get to minus 12 you're at 70, and then you're basically at 100% once you get to minus 15. There's also another check here to ensure that the lowest 1 kilometer has an RH greater than or equal to 85%. And that's basically ensuring that you have some deep enough layer to get precipitation going, whether that's a drizzle, it could be a rain, just something like that. If that's not present, we're going to assign 100. And this is specifically important so that we could put prob ice present on a cron, i.e. to be always populated, and make that work. There's more documentation on the prob ice present method and how it's calculated in the probability weather type documentation. So let's take a quick look at this on a grid. On the left, this is actually a true example. What you have coming out of this event, if you go into Iowa, where the values are 100 there, that represents too dry of an air mass to actually generate any kind of precipitation. That check for the bottom 1 kilometer having RH 85% fails. And so again, that's too dry, so you get a 100 value. As you work your way northeast into western Wisconsin, the values drop off to 0. And that's the perfect environment that the prob ice is used for, where you've got a deep enough layer near the ground to allow for, maybe at least some drizzle production. Maybe you even get it deeper for rain, but in this case it's a drizzle production. But then you move higher up and you get towards the snow growth zone, and that's still dry relative to the RH respect to ice. Even farther up, you go up higher towards 400 millibars. It's really, really dry. So again, you get a 0 value in this zone. Go farther northeast, all the way up into northeast Wisconsin, and here we get a 100 value. But instead of the situation earlier in Iowa where it was too dry, now we've got the situation where it's favorable for snow. We've got plenty of RH into the snow growth zone. We've got ice being generated, so you get 100% value. The other grid here that can manipulate the precipitation type from the max wet bubble loft is the prob refreeze sleet grid. The definition for this is a probability that that liquid from a loft, underscore liquid here, can refreeze to sleet. And an example of that here is shown on the right, and this was actually observed that was occurring. There was sleet happening at this time on that day. You must have max wet bubble loft grid greater than 3 Celsius, at least the points there, to ensure liquid. Generally, this is going to be a rare grid to edit because the conditions to have, for sure having liquid and then having a deep enough layer to allow for refreeze and to be cold enough, somewhere around -6 to -8 is where you really start to get that refreeze sleep process going with a 2,500 foot depth. The observed values can be found via a combination of surface data with RAYOB and AMDAR data, as well as dual pol. So how is this computed? Again, kind of referencing this earlier, that you check for a cold dome that is at least 2,500 feet thick and colder than -2 Celsius. The probabilities only start at 10% there with that situation, but as you get towards -6 and then -8, those probabilities rapidly increase. And here's an actual chart showing that increase in probability. See the documentation for the probability weather type methodology for more details. It's also, the documentation is in the forecast builder. So here's an example of prob refreeze sleet. This is from the December 1st, 2007 case where the La Crosse area was hit both by sleet being produced just by hydrometers partially melting through the max temperature aloft, and then refreezing when the max wet bubble aloft got warm enough, and you ended up with refreezing to sleet. So La Crosse ended up with about 2 inches of sleet out of this event, being hit by 2 different cases of how to produce sleet. Finally, there's one other grid. It's definitely an optional one here, called road temp. And for this grid, there's 2 different situations where it can be helpful. Let's say your forecast or you're experiencing rain because the air temperature, say like 34. Just take that for example. But you've been in a long period of cold, and your road surfaces, other objects are still, they're taking a while to warm up. Take like a case of having rain in January in the northern plains, for example. The surfaces are going to be really cold. So in these situations, what you'd want to do is assign a road temperature value less than or equal to 32, and what that will do is copy your rain probabilities to freezing rain. Now on the reverse, let's say you're having freezing rain because your temperatures are like 31 or so outside. But you're in late spring here. The solar radiation is stronger, warms the roads up quicker. So in these situations, just assign the road temperature a value greater than 32. And this will result in freezing rain copy to rain. So you get kind of equal chances for either rain or freezing rain. And in both situations, you'll get at least some ice accumulation in the forecast, but not as heavy as you would if you didn't follow this process. IRIS can show some of the observed road temperature values for those states that have road temperatures set up. There's also this website address here. It's referenced in Forecast Builder as well, where you can grab forecast values for road temperature. A few additional top-down notes. Note that your hourly temperatures and dew points. Dew points are important here. Will help separate your rain from freezing rain. And this all comes out of the freezing rain accumulation ice model. Now, if your max sweepable aloft is less than or equal to 0C, the precipitation type situation is assumed to be a rain-snow. Note that even in a rain-snow situation, you can produce freezing rain if your prob ice present grids depict a loss of ice in the cloud. And there have been observed cases of this happening. Deep slightly above freezing isothermal layer. Should your max sweepable aloft be greater than or equal to 1 Celsius and your temperature is greater than 32, the precipitation type is just going to go to rain. So again, some slight modification to the process that you've learned up to this point, and this is again to handle some specific situations. Should note that in these isothermal layer cases that you can still get freezing rain in this scenario, and this goes back to the first bullet above, that if your temperature is between 32 and 35 and your surface wet bulb is 32 or below, you're going to get freezing rain. And that's also been observed. And here's kind of an example of that layer that your max wet bulb is equal to 1C and temperature is greater than 32. So this would be a rain sound. And if we did not have this check in there, the max wet bulb aloft curve would have suggested mostly snow, maybe a little bit of sleet mixed in. So this is like a little QC check. Some quick example output. This is from the December 1st, 2007 storm, and you can see all three top-down grids were incorporated here, not the road temperature, but just the normal three top-down ones. And see how these are all derived, no human editing required. So in summary, the top-down approach here provides many benefits. It's a quick and meteorological sound way of developing precipitation type forecasts. What's nice too, you can blend models along in the process, no restriction to a single model. And your ability to handle scenarios more quickly when no models are handling the weather correctly. If, for example, you're seeing some rain, but your max wet bulb aloft was only 2 or something, and none of the models are getting up towards like 3 or 4, well, I could either push my max wet bulb aloft up towards 4, or I can adjust the prob ice present to get to 4. In the Forecast Builder training, there's a module about how to adjust your precipitation type to something else. Nice thing too, the top-down approach can handle situations where icing is only occurring on roads. And for your information, there's more on that 2007 December 1st case at the website listed there. And thank you for watching.